All right, so welcome back, everybody. Last video, what we're going to do is look at other ways that we can calculate delta S and delta G, other than using that equation which we've been using, delta G equals delta H minus T delta S. So first I'm going to talk about ways that we get delta S. So remember delta S being entropy. So in general, when a reaction involves gaseous molecules, the change in positional entropy is dominated by the relative number of molecules of gases, reactants, and products. So how we determine first if delta S is positive or negative is we ask ourselves, do we have more products? And if we have more products, in the gaseous state, our delta S is positive because we're becoming more disorganized. So if the number of molecules of the gaseous products is greater than the number of molecules of gaseous reactants, positional entropy increases and delta S is positive. So looking at this reaction, we have one reactant that is a solid producing two reactants, one a solid and one a gas, so our delta S obviously here is positive. All right, so in thermodynamics, it is the change that we're going to be looking at. So it is the change in a certain function that is important. So change in enthalpy determines if a reaction is endothermic or exothermic, negative delta H being exothermic and positive delta H being endothermic. And our free energy, our change in free energy determines if it is spontaneous or not at constant temp and pressure. So this is important because absolute values for many thermodynamic characteristic systems like enthalpy and free energy cannot be determined. However, we can assign an absolute entropy value. So consider a perfect crystal. And again, entropy describing disorder. If I have a perfect crystal at 0 Kelvin, all molecular motion has stopped, and the crystal is perfectly organized. So molecular motion has stopped, and if it's a perfect crystal, its internal arrangement is absolutely regular, meaning every particle must be in place. So for this perfect crystal at 0 Kelvin, and again, this is completely theoretical, our entropy is 0, and that's our third law of thermodynamics. The entropy of a perfect crystal at 0 kelvins is 0. All right, so quick question. The lowest possible entropy achievable occurs at, what would you say? Give you a second to read these. And hopefully you said C, in a perfect crystal at 0 Kelvin. And that's just something you should have memorized, that third law of thermodynamics. And what that kind of looks like, kind of this. Here we have this perfect organization. So as temp increases, disorder increases. The molecules start moving and our disorder starts becoming greater. It becomes more disorganized. All right, so since S is 0 for a perfect crystal at 0 Kelvin, entropy values for a substance at a particular temp can be calculated by knowing the temperature dependence of entropy. We're not going to calculate it, we're just going to look it up on a table, but that's how scientists can determine this delta S value. So the standard entropy values, delta S, at 298 Kelvin and 1 atmosphere of many common substances are found in Appendix 4. It's in your book or it's on that same sheet that we've been using to look up the delta H values of common substances. Delta S, if we look here, for diamond is very low because a diamond is highly organized. And we can look at different S values, okay, our entropy values for different other substances right here. And you can find plenty more on that Appendix 4 handout that you all have. All right, so what is another way that we can determine delta S than that equation that we've been using? Well, we can also use Hess's law. Because delta S, entropy, is a state function, it doesn't matter how we get there. So we can just, again, take our products completely apart, reorganize them, and look at the entropy change. So entropy, again, is dependent on the number of moles. And generally, the more complex the molecule is, the higher the state of the entropy value. So what we're looking at here, again, is the entropy of our products compared to the entropy of our reactants. We're taking them apart, we're putting them back together, and calculating our overall change in entropy. So, delta S at 25 degrees Celsius for this reaction. How can we calculate that? Using Hess's law. Again, please remember this variable right here, N, is number of moles. So we do need to take that number of moles into account into account. In this case, things like oxygen that are in their elemental state still have some disorder, so they are going to have an S value. So please, again, in this case, make sure that you're not just ignoring elemental substances, but you're actually looking up the S values of all of these substances. So I take my products minus my reactants, and 248 is that of SO2. I multiply that by 2. 38 is that of NiO. Multiply that by 2, minus my reactants, 53, that of NiS, and 205, that of oxygen, multiplied by, again, their number of moles. So products minus reactants. That's going to become a very important equation in this unit as well. What you'd end up getting is a negative 194 joules per Kelvin, okay, would be your unit for delta S. So just another way that you can calculate delta S using Hess's law. All right, so what we're also going to look at is delta G. So delta G is the change in free energy that will occur if the reactants in their standard states are converted to their products in their standard state. So we're also going to look at other ways that I can calculate delta G being free energy. For example, this equation. Here is my delta G value. Again, what can I look this up in? I can look this up on the table. If you look on the table, you are given values for delta H, delta S, and delta G. So this delta G represents the change in free energy that it takes to go from 1 mole of nitrogen reacting with 3 moles of hydrogen to produce ammonia, okay, 2 moles of gaseous ammonia, and this is our delta G for that we can, again, look up in a table. So delta G cannot be measured directly. It is calculated from other measured quantities and then placed on the table that you're going to look up. So it allows us to compare the relative tendencies for these reactions to occur, remembering that if it's negative, it happens spontaneously. So the more negative the value for delta G, the farther the reaction will proceed to the right in the forward direction. If delta G is positive, it's spontaneous in the reverse, left direction. So the more negative, the farther to the right the reaction will proceed to reach that equilibrium. Equilibrium being at the lowest possible free energy position for a reaction, which may not always lie completely to the right. It may be at a lower energy state if I'm at an equilibrium where there are some reactants and some products, which is kind of shown in this diagram right here. So for reactions, not phase changes, it's not going to completely go all the way to the right. Like in a phase change, all of the liquid may evaporate to a gas if you let it occur for a long enough period of time. But for reactions, again, there may be a lower energy state like we see here where all of the reactants haven't been converted to products, but we're still at the lowest free energy state. It's reached what is called equilibrium, where some reactants and some products remain. So, method 1 for calculating delta G is this equation right here. We're all familiar with it. We've used it. We've done 5.9, or at least most of it, and we're comfortable hopefully using this equation. How else can we calculate delta G? Is we can use an adaptation of Hess's law. So we can look up the delta G for various reactions and add them up to get the overall delta G. So what we're looking at is these two reactions can be added together to get this reaction. Again, we're going to do the same thing we've been doing with Hess's law and delta H. It's just now we're going to apply that to delta G. So I want these two reactions, reaction 1 and 2, to add up to reaction 3 right here. So what am I going to do? Diamond is on the right side, so I'm not going to flip a reaction 1. I'm going to keep it as is. Reaction 2, graphite, solid graphite, carbon, needs to be on the product side. So what do I do to reaction 2? Flip it. I don't need to multiply it by anything. I just flip it. And what do I do to my symbol for delta G? I flip it as well. So then what do I do? Simply add them up. Delta G plus delta G, okay, delta G of reaction 1 plus delta G of reaction 2 gives me my overall delta G. So does this reaction occur spontaneously? Yes. So all of your diamonds that you buy will eventually be graphite. Again, this doesn't tell me the rate of the reaction, but it does tell me that it occurs spontaneously. So when you buy a diamond, eventually it will be graphite, but again, it won't be in your lifetime or any of your children's lifetime. It takes a long time for a diamond to decompose to graphite, but it does happen spontaneously. Okay, and that's what this tells us right here. So that's another method that we can use to calculate delta G. We're going to look at method 3 also for calculating delta G, and that's the same that we used to calculate delta S earlier. The change in free energy that accompanies the formation of 1 mole of that substance from its constituent elements with all reactants and products in their standard states. So what we can do, what is this saying? This is saying you take products minus reactants again. Okay, so this is my overall equation that I can also use to calculate delta G. Which method are you going to use? Well, that depends on what variables you're given. Okay, and then you're going to choose which method to use. All right, so in this case, delta G of an element in its standard state is 0. So you are going to have plenty of zeros here. All right, so here we have methane thiol is a high-octane fuel used in high-performance racing engines. Calculate delta G for this reaction using your delta G's from Appendix 4. In this case, I just give you the delta G's in the table right here. So what are we going to do? Take products minus reactants, also remembering to take number of moles into account. So if you want to, pause the video, practice this on your own, and then check your work. So pause. I'm just going to wait a second and then go ahead and explain. So in this case, again, we take our products minus our reactants, taking into account how many moles there are. Notice our only elemental substance is oxygen with its delta G of 0. Most of the time that would be given to you, or you could look it up on the table, but if it is not and you notice something is in its elemental form, you can assume it is 0. So in this case, I take my products, CO2, which is 394 times 2, add that to H2O, negative 229 times 4, minus my reactants, methanol, negative 163 times 2, and add that to oxygen, but oxygen, of course, is 0. So I take my products minus my reactants, taking into account how many moles there are, and again, I get negative 1,378. So that's another way that I can calculate delta G. All right, large delta G, very favorable. This is a very favorable thermodynamically favored reaction, okay? And this is when I burn methane thiol. Obviously, it happens as long as I add that activation energy. It does burn. All right, so that is the end of today's lesson. Your homework, reading a note 16.1 through 16.9 if you choose to do so, but please do both worksheets. The worksheet from last class, 5.9, finish that, and then try to finish worksheet 5.10, which is on sections 16.5 through 16.9. This is one of 2 worksheets you'll get on that section. So if you have any questions, save them for next class. The answer key for both worksheets is posted on the website. Hopefully these videos helped, and have a good day, and I'll see you tomorrow.